Welcome to this explainer. Today, we're diving deep into the anatomy of an exploit, but we're doing it with an alchemist mindset. Why? Because we're looking at a massive paradigm shift in our industry. We're talking about how probabilistic AI completely breaks and reshapes our entire cybersecurity stack. Look, if you're used to securing networks just by patching deterministic code or checking access controls, buckle up. We're navigating a landscape where exploits are purely behavioral, attacks can literally be invisible, and the models you're trying to lock down, they change their responses every single time you ask them a question. It's wild. So here is our scope of engagement for today. We're going to cover what is AI red teaming, the AI threat landscape, state-of-the-art jailbreaks, system-level open questions, and finally, the future of AI security. Let's get right into it. Section 1. What exactly is AI red teaming? Okay, the absolute crucial point here is the contrast. Traditional security, it targets static infrastructure and access controls. You're basically looking for a crack in a brick wall, right? A deterministic flaw. But AI red teaming, you have to target dynamic behaviors, tool call chains, and the underlying probabilistic nature of the model itself. Because with an LLM, the system is fundamentally statistical. Think about it. How do you patch a behavior? A perfectly secure codebase doesn't mean a secure model if the training data is poisoned or if the model's linguistic boundaries can just be completely subverted. We're no longer just testing for unauthorized access. We're actively hunting for exploitable behavior across prompts, tools, and retrieval flows. Moving on to Section 2, the AI threat landscape. So if we look at the OWASP 2026 framework, it becomes super clear that we aren't just attacking a single endpoint anymore. Look at these categories. We're testing autonomous behaviors. Take memory poisoning, for example. Imagine a long-running customer service chatbot session. An attacker subtly injects some malicious context early on just to slowly, quietly manipulate that agent's behavior over time. It's insidious. And we're also dealing with insecure inter-agent communication, where one AI might actually pass an exploit to another AI, accidentally or maliciously. The attack surface has completely blown up, moving from standard code infrastructure straight into cognitive and behavioral manipulation. And this perfectly illustrates the Cloud Security Alliance's Maestro framework. It completely separates your pure machine learning gaps from interaction-based gaps. On the left side, you've got your classic ML attacks, right? Data poisoning, evasion attacks, basically crafting inputs to fool the model. Standard stuff. But on the right, this is where it gets crazy. Interaction-based gaps. This is where multiple AI agents might secretly collude with each other, or where they're competing for resources and inadvertently create a massive harmful outcome. It is a completely new dimension of threat modeling. We really have to start thinking about how these AI agents interact with each other out in the wild. All right, Section 3, State-of-the-Art Jailbreaks. Let's zoom way in on the absolute state-of-the-art techniques. Honestly, forget those basic prompt injections we saw back in 2023. Right now, attackers are bypassing defenses without leaving a single visible trace. Recent research has actually proven that prompt-based defenses are fundamentally flawed. Why? Because attackers are pulling off what's called imperceptible jailbreaks. They're doing this using invisible Unicode characters. Standard jailbreaks assume you need to visibly modify a prompt to trick the model, right? Well, researchers found that by appending invisible Unicode variation selectors, which, by the way, are usually just used to change the color of emojis, attackers can completely subvert the tokenizer. And the text, it remains visually identical to the naked eye. No way you'd spot it. Seriously, to a human pen tester or even your standard heuristic filter, this input looks like a perfectly normal, 100% safe request. If you're digging through logs trying to figure out why your AI went off the rails, or if your security filters are just scanning for suspicious words, this prompt is going to pass right through. It looks completely innocent. But when we compare what the human sees to how the LLM tokenizer secretly reads it, a massive, massive vulnerability is exposed. Attackers have basically tacked on these Unicode variation selectors, like U plus FE0F. Now, these are invisible characters, but they occupy real textual space that the AI's tokenizer still processes. They secretly alter the input array. This effectively creates an invisible adversarial suffix that completely scrambles the model's safety alignment and literally forces it to generate restricted content. And it entirely bypasses human oversight. It's brilliant but terrifying. And look, they aren't just blindly guessing which invisible tokens to use here. Attackers are actively leveraging hardcore mathematical optimization techniques, things like greedy coordinate gradients and chain of search pipelines, to automatically generate these invisible adversarial suffixes at scale. Think of it like mathematically reverse engineering a LOX combination, almost instantly. What they're doing is maximizing the log likelihood of target start tokens, basically forcing the model to start its sentence with a word like sure. That simple action redirects the model's attention entirely away from its safety training. It is an automated, mathematically optimized attack right on the model's linguistic boundaries. Section 4, System-Level Open Questions. So, a really major open question we're facing right now is that safety training inherently suffers from competing objectives. This research from the paper Jailbroken hits the nail on the head. Model capability directly contradicts safety restrictions. It's a paradox. The smarter and more capable you make a model, the more complex the pathways it can find to just bypass its own safety rails. So what does this mean for us? It means simply scaling up models, just throwing more compute or more data at the problem won't magically fix security. If anything, it might actually make your attack surface even wider. And we get to supply chain security, which is just a massive unresolved issue right now. We aren't just downloading code libraries anymore. We are downloading massive opaque matrices of numbers. Researchers have actually theorized the existence of undetectable Trojans hidden deep inside model weights. Think about that. If an attacker poisons a foundational open-source model, that exploit can persist through fine-tuning, through safety training, turning our open-source dependencies into literal ticking time bombs that can be triggered on demand. And because they're mathematically obfuscated within the weights themselves, you absolutely cannot just audit them like traditional software. Bringing us to Section 5, the future of AI security. Okay, so how exactly do we defend an enterprise ecosystem when the attacks are mathematically generated, visually invisible, and the models themselves are fundamentally probabilistic? While the industry is shifting rapidly, we're moving away from manual penetration testing and going straight toward continuous, developer-integrated scanning tools. We're talking frameworks like Microsoft's Pirate, PromptFu, and NVIDIA's Garak leading the charge here. These tools integrate right into CI/CD pipelines, which allows organizations to scan for prompt injections, data leaks, and those multi-turn jailbreaks before a model ever even hits production. You literally have to test AI at the speed of code deployment. And all this developer-integrated tooling eventually builds up to what we call CART, or continuous automated red teaming. Because let's face it, the attack surface is just way too large for humans to probe manually anymore. So we're seeing the rise of these automated loops. You deploy an attacker model, right? It generates thousands of adversarial probes. The target model responds. And then a totally separate judge model evaluates those responses to see if a jailbreak was actually successful. This entire loop operates relentlessly at machine speed, constantly mapping out the shifting vulnerabilities of your probabilistic system. But hey, just finding the flaws isn't going to cut it. To truly secure the entire AI stack, organizations have to evolve toward violet teaming. This is all about pairing the aggressive adversarial discovery of behavioral vulnerabilities, your red team, with immediate systemic remediation strategies and runtime guardrails, your blue team. Red plus blue makes violet. It's an integrated, fully holistic approach that directly addresses emergent risks across the entire socio-technical system. I'm going to leave you with this final thought to take away from our explainer today. If scaling models won't natively fix security, and prompt-based defenses are fundamentally flawed against invisible tokenizer exploits, is your organization ready to test its AI like an alchemist? You can't rely on static defenses anymore. We have to continuously probe the unknown. Thanks so much for joining me on this deep dive into AI red teaming. I hope this gives you the actionable insights you really need to secure your AI pipelines out there.